In this problem, we are given the SN1 reaction that's shown here, and we're asked to do a bunch of things. First, to show a curved arrow mechanism. Next, to draw an energy diagram with labeled axes, including the reactants, the products, the energy of activation, and the delta H. And we're told that the starting material and the products are about equal in energy. We're asked to draw the transition state, if there is one, and then the rate equation, and then how the rate changes in the following conditions. So, first things first, we can start with our curved arrow mechanism. I'm going to redraw it just below and a little bit smaller. So here is our starting material. And we remember the first step in any SN1 reaction is to have the leaving group leave. So our iodine is going to leave. And now we'll have our carbocation intermediate and our iodine that's left. Then our solvent, water, or our weak nucleophile, is going to come in and it will attack. And it can go front or back, but it'll form a racemic mixture if this were a stereocenter, but it's not because those methyl groups are equivalent. And that is the arrow pushing mechanism for this. Next, we're going to draw our energy diagram. I'm going to draw my kind of rough graph here. And on the y-axis, we're going to have our energy, and the x-axis will be our reaction progress. That axis can go by a number of names, including time, just reaction. I like reaction progress. Now, since we're told that the starting material and the products are about equal in energy, I'm going to draw them sort of arbitrarily about here. Then I'm going to draw my starting material, which is just our alkyl halide. And our final product is going to be the water substituted alkyl chain. Now, because this is an SN2 reaction, we're going to have two bumps of energy. That's because we have to overcome the energy to make our leaving group leave, and then again for our attacking group to attack. So I'm going to draw this going up and down, and then up again, and then down. So because we have two peaks, we're going to have two transition states and an intermediate in this energy well here. The first transition state is where our leaving group is in the middle of leaving. So I'm going to draw this in a different color just to try to make it even clearer. And I'm going to be a little bit more explicit with my groups here. So our iodine is leaving, so we want to show this as a partial bond. That is our first transition state there. We'll make sure that we got the right number of atoms, and we can also show the partial charges that are forming here, like that. Those are our deltas to show the partial charge. Next, we have our other transition state here. That's where the oxygen bond is starting to form. And it'll look similar. We're going to have our carbon in its chain, and then the partial bond to the oxygen. And again, with our charges, we're going to show a partial positive on that oxygen as it is slowly taking on a positive charge, and our carbon actually still has a partial positive charge because it is partially losing the positive charge from that carbocation. So it's a little unusual here in the grand scheme of chemistry, I suppose. Now, it's not listed here, but it just feels right to draw. In this well here, we would have our intermediate. Okay, now we have our energy of activation and our delta H to draw. Our energy of activation, I'll say E of A1 is that first hump there. E of A2 is much smaller. It's going to be that bump there. Our delta H is going to be, our total delta H is the difference between the energy level of the starting material and the products. Since there is no difference, our total delta H would be 0. In all likelihood, it would probably be some small number. It wouldn't be exactly 0, but we are told that they were equal in energy, and so it would be 0 for this. If we wanted to show a smaller delta H, that's going to be difference here between the starting material and the energy level of the product. Of the intermediate, at least, this would be, I might call that delta HI for the intermediate. And then if you wanted to show a delta H from the intermediate to the finals, maybe we'll call this 1 and this 2, and then we would have delta H2 to show the difference between the two different steps in this reaction. So, we got our transition states. Next, we're going to talk about the rate equation. The rate equation for any SN2 reaction is always just based on the alkyl halide. So I'm going to abbreviate this Rx. And that's it. That's our rate equation. Now, let's talk about how the rate changes. So if we were to change the leaving group from an iodine to a chlorine, we would be putting on a worse leaving group than our iodine. Iodine is a better leaving group than chlorine because it's larger and more polarizable. So, because we would be putting on a worse leaving group, though chlorine is still a pretty good leaving group, it's just worse than iodine, we would be decreasing the rate of the reaction. Next, we changed our solvent from H2O to DMF. We would be changing from a protic solvent to an aprotic solvent. We remember that protic solvents are better for SN1 reactions. They help facilitate them. And so switching to an aprotic solvent wouldn't help at all, and that would be, again, decreasing our rate. Next, if we were to change our alkyl halide from the original structure here to a different structure here, how would that affect the rate? Well, let's look at the carbocation center here. We have a tertiary center on our original structure, and then it got changed to a secondary center. Secondary carbocations are less stable than tertiary carbocations, and so we would see a decrease in the rate because there would be more energy that would need to be put in, and it would be a higher energy intermediate. Next, we're going to ask, how does the rate change if our alkyl halide, the concentration of that is increased by a factor of 5, and the concentration of water is increased by a factor of 5? That sentence doesn't even make sense to me. The concentration of water when the solvent is water, that's just silly. And we already know that the rate equation for an SN1 doesn't matter how much solvent you have. The rate is based only on the slow step, the loss of the leaving group, and the concentration of your alkyl halide then. So we may as well just cross that out. Doesn't matter, doesn't have an effect. So if the concentration of our alkyl halide is increased by a factor of 5, that means the rate of our reaction will be increased by a factor of 5, specifically. And that is how we attack this complex problem.